basically consists of these four parts. One is the variables, constants, data objects. Then, so in this part, we define the location of the point. Okay, the point P1. This is motion control, simply move or move or approach and depart. This is open close, and this is program control, if then else statement or some logical statement. So using this four, we'll be writing a program to do some tasks. So today in the lab also, one of the experiments is this, that you're supposed to write a program yourself to do something. Okay. No, program control is basically the logical statement. Say, for example, if then else statement, or go to subroutine, come back. That's the program control. Basically, the sequence in which the program is being executed. Okay. So, yeah. So, this is signal. So we can look at a very simple example before we go on. So this is a very simple example. So this is a Puma robot. This is the same Puma robot that we have in the lab. So it has 6 degrees of freedom. The first degree of freedom is here. This is called the waist. Then the second is the shoulder. Third is the elbow. The roll pitch yaw is at the wrist. Okay. Yeah. So the 0, 0 of the robot is here. Okay, so z-axis is this side. This is x-axis, y-axis, that is z. That's my global frame. This is so the task is essentially to pick up one part from here, okay, and then go and drop it. Okay. So the task of the robot is to pick up one part from here, then go and drop it at that point. This is the top view of this is shown here. But we need the coordinates of the point, so we need these details. So the pellet details are given here. So there is one part. There are 4 by 3, and this is the dimensions of where the object is kept. So the logic that will be followed is that first we have to define the point. So what we'll do is we'll define, so what is known here, what is not known. The robot is fixed on a table, and with reference to the x, y, z of the 0, 0 of the robot, we need to know the coordinate of that corner point or start point in terms of this. So the corner point is already known, it is taught. We will see how. Okay, so this corner point is taught means the position and orientation of that point is taught. Then with reference to this, I can shift the corner point to the top of this. So when I catch an object, I basically have to go there and position my gripper, then go down, catch it, move up, and then go there. So it basically means as far as the corner is considered, if I teach this point, the rest of the centers are fixed because I know this distance and I know this distance. So we'll simply go to the corner and shift it by this much and this much. Okay. So then we'll pick up one, then we'll index the corner point, bring it to here, catch this, drop it there, then index it again, come here, pick it up, bring it there. So basically I need to know only one point, that is the corner. The rest of it is known because the dimensions are known. Now what is done in robot programming or in any program is that there is a good way of writing a program and there is a bad way of writing a program. The program can be written in many ways. A bad way of writing a program is go to this point, index it here, catch this, drop it there, then go to this point, index it, go here, catch it, drop it, then go to this point, catch it, drop it, then go to this, index it, go here, catch it, drop it, and keep doing that. So you have one line, another line, another line, another line, so all like that going in one line. That's a bad way of writing a program. Why? Because the number of parts could be very large. In that case, you'll have that many lines. Each one is indexing, then going here, then catching, then coming back. Okay. A good way would be that if you can write a function or you can write a subprogram. Now that would have the advantage that if you're changing the palette number of parts, for example, all you need to do is just change something in a subprogram. The rest of the program remains the same. So the way robot programs are written these days is essentially to have each task as a function or a subprogram. For example, spot welding, spray painting, pick and place. So whenever the programmer needs to do some task, he will simply refer to that subprogram, call it, do the function, and then come back to the main program again. So what we'll be doing here is we'll be writing a subprogram for indexing. So we are teaching the corner, then we are simply indexing. Indexing means bringing the corner to the top here, catching this, dropping it, then bring it there, then bring it there, there, in that order. Okay. So we start the program like this. So the first thing that's important here is how many rows and how many columns are there. Why? Because this is a variable, so the palette size could change. So the same program will work. So we need to define how many rows are there. There are 3 rows and there are 4 columns. So the first thing we define here is we define the number of max col is the number of columns and max row is the number of rows. So if I change the number of rows and columns, the program will still work. Next is I start from row 1 and column 1, which I'm choosing the first column. Then what we are doing is we are setting the pick point. This is a variable name, pick point, which is equal to the coordinate of the corner point. So I'm assuming that the corner point and the locations are already taught either by t-spendent or by using here command. So this first point, corner point, is taught. Then I shift the pick. Then I shift the pick point. Then what we do is we shift the pick point by the distance. Yeah. So we set the corner point of the indexing table. Then I shift it by 20 minus 20 60, which means if I come back here, it basically means that my corner point was there. Then I shifted by 20 this side, minus 20 this side. Y is minus, so it comes here. Okay. And 60 is assuming the height of the object is maybe 20. Then I shift it to somewhere on top. Okay. So from the corner, I've shifted by 20, minus 20, and 60 in the z direction. So somewhere there. Okay. Then what we do is we open eye. Okay. So after I've shifted the pick to the top of the first object, I'm using open eye now. Okay. So open eye means it will open immediate, and then only it will go to the next. The next command is move pick. So the general commands that are used is open, move, close. These are the general commands used. So move pick, it goes to the top of the first object. Then it draw means 0, 0. Minus 25 means it goes down. So I could have said, I could have also said draw command they're using here. We could have used moves if I'm defining the CG of the object. Here they're not defining the CG of the object. They're simply moving this down by 0, 0, minus 25. Then close eye, which is again closed loop. Then draw is 0, 0, 25 in the upward direction. So after coming down, it is going up. Then move to the cute point. So the cute point is here. So it was corner point was here. It was shifted here to the top. Then I draw it down, close it, take it up. Then I move it to that point, and then I drop it and come. So we go to move point, then open eye. It drops it there. Then I want to index it. The first fellow is gone now. So I want to index it. So it goes to go sub, a subroutine or a subprogram called palette. So this is the subprogram called palette. So from here it goes there. Now what it does in palette is it increases the column by one. So it becomes column plus 1. We started with 1, it makes it 1 plus 1. Now it makes it 1 plus 1 equal to 2, and then checks if it has exceeded the maximum number of columns. Okay. If it has exceeded the maximum number of columns, then go to 20. Go to 20 is here. Then what it does is it increments the row there. Okay. So it makes it row plus 1. So in our case, the first one, second one is 2, so it is not exceeding 4. So now you are shifting the pick again by 50, 0, 0. So the point was here. Now I shift it by 50. So this is my 50. So I shift the pick point from here to there. Okay. Then I go back to the main program and go to 10. So 10 is there. It goes back there. So it picks up that object, goes on top, goes down, catches it, okay, and closes it, goes up, moves to the cute point, drops it, and then comes back here. Okay. So this is the subprogram which is doing the indexing. So the way the indexing is being done is it is going like this, like this, like this, like this. The moment column is exceeding 4, it is starting from here now. Then it will take this one, this one, this one, this one. Then it will come here, this one, this one, this one. And then it will go back and end the program. Okay. So if it is exceeding both the rows and the columns, so column is 4 and row is 3. If it is exceeding both, then it will simply go back to 30 and it will end the program. Okay. Yeah. It is assuming that it is somewhere here, and if you come by 25, you can catch this object. That is taken care of. Yeah, yeah, yeah. So that is taken care of. So basically, we are teaching it only one point, and then we are indexing this point to come here, 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 like that, using the subprogram. Yeah. So we are teaching one point. Which point we are teaching? The corner point. So the corner point is this one. Okay. So I want to catch an object. To catch an object, you have to go to the CG and the top of the object. So I'm shifting the corner by 20. So this is 20. That is 20 dimension. So it is plus 20 minus 20, and 60 is height in terms of from here till there is 60. So each time I'm shifting it by x, y, and z. So if you look at the coordinate system here, it is x, y, and z. That's my 0 frame. Okay. So using very simple commands like, so we can see that very, very simple commands have been used, almost English-like. There's nothing to remember here, nothing to do. Anybody can do it in first shot only. Okay. So the manufacturer has intentionally made the program to be simple, so that anybody can actually program the robot and use it. So they don't have to go into assembly language and all those kind of things. Okay, so this is an example of a robot, a 6-axis robot, where we have to do the experiment also. So we'll be using simple commands like open, move, close, open, approach, depart, and then you can write the program. So this we'll do an experiment, and then you have to write the program by yourself. So you can make it do different things. For example, you can make it draw a circle, you can make it draw a rectangle, do all kinds of motions. Okay. So simply by using this set of commands. Okay. So we can also write a program for this one with some sensor interfacing. So in the previous program, there was no sensor interfacing. So we can simply use commands like sensor 1, sensor 2, on, off, and then to indicate when the part has come, when the robot has picked up the part. So when there is a conveyor also, when the part is coming on the conveyor, the moment we can put a sensor here, the sensor will sense this, and the moment the part comes, it can say signal 1 is high. The robot understands the part has come, it will pick it up and put it there. Okay? So that program also can be written, or we can simply we can add those few lines onto that program. This is a little bit more, so the programs can get a little bit more and more complicated. This is a more complicated program where there is a parts carousel, and there is a sensor to detect the arrival of the parts. So after the detection is, after the part arrives, then it informs the robot. The robot picks it up and puts it into this work table. Okay. Now after machining is over, again this table has to tell this robot, it will pick it up and put it here. Okay. After machining is done here, then it will take it up and put it here. Now in this, there is a sequence of operation, plus there are times of machining. Okay. So we have to sequence those times now. Otherwise what will happen is they will end up with a deadlock now. So if this is doing machining, that is doing machining, and the robot also picks up one part from here. Now it has no way it can pick that up and pick that up also. Okay. So when there is multiple machines, multiple times involved, then it becomes difficult to sequence. Okay. And that is where the real challenge in programming is. And that is also why it is so expensive. Now if we have multiple robots, this is only case of one robot. So in industrial applications, there will be 5, 6 robots working together or more. In such cases, what is done, so if you're looking here, in this example, there are 3 robots which are doing spot welding. Now, in a car body, in the chassis, in the car, the sheet metal is put on top. And the sheet metal is welded onto the chassis by means of spot welds. Now, the location of the spot welds they are all over the car, in all directions, under the car, on top, side, inside. So the robots actually have to go inside also sometimes and do welding. Now the number of welds it can do per minute is very, very high. So if you look at, so each car has about 3,000 to 4,000 welds, just one car. So to make 4,000 welds, if a human being is doing, it will take a very long time. Whereas if a robot is doing, if 5 or 6 robots are doing in 5 minutes, they can do it. So the speed at which they work is about 10 to 15 seconds per weld. That is the speed. So that they can do a large number of welds in a very, very short time. And that is one of the reasons where spot welding robots are used in automobile industry extensively. Spray painting, spot welding, and assembly. These 2 tasks. Now, if you're trying to program this kind of a robot, although it appears that programming is very easy, well, actually it's not. Because if you try and program for this, not only must it get inside very complicated spaces, but it should also avoid, not hit the object, not interfere with the other robots which are operating. And on top of that, your cycle time should be optimal. Okay. Because little bit delay also causes problem, it causes a lot of change in the large number of cycles. So this is the reason why robot programming is very, very specialized. And the people do not, normally the people, for example, Tata Motors, when they do this spot welding, their plant is a Nissan plant. And it is programming and everything is already done. So they don't change anything. So normal cases and applications of industries, the programming and the maintenance of the software is the one that adds to the cost, and normally the people in the industry will not do it. So they are specialized people who will do it. Now the way it is done is we talked about kinematics. To go into very complicated spaces, you need very, very complex kinematics now, okay, because it has to go in such a way that it has to be optimal, and it must not hit anything and not interfere with somebody else. Okay, so that means that the kinematics is not easy. So as we'll go along, we'll see how to do kinematics of that type. The second is if how this programming is actually done in the industry is that they would have a CAD model of this. So they would initially have a CAD model of the car, CAD model of the robots, and the full cycle time will be optimized on the CAD model first. Okay? So in simulation, they'll be optimizing the cycle times, that which weld is to be done where, what is the cycle of the weld, what's the direction of the weld. And then what they will do is they will come to the real world. Now, once they come to the real world, again, without the car body, they will run the robot and then see whether it's working properly or not. Then what they would do is they'll make a dummy of the car model that is not using metal, but using plastic or using wood, so that if there is some error somewhere, it will not damage this or will not damage that one. So after the third step or the fourth step, when everything is sure and they are sure that the cycle is optimized, only then the real car body comes and then the actual assembly takes place. Okay? So this takes a lot of time. It takes a real lot of time. And this is the one that adds to the cost. So in a robotic assembly system, the robot is not very expensive. It's only about 20%. 80% is the software optimization time. Then in terms of upgrading the software, giving the guarantees, all that. So automation, in a way, is not expensive in terms of the mechanical hardware structure, but it has become expensive in terms of the other things. Okay? Because writing a program and ensuring that everything is done correctly, that is the one that is expensive one. Okay? So if you go to Tata Motors and if you see the program running, the robot program, you go to any industry, very often you'll find that if the robot is Japanese, then the program is also written in Japanese. So those poor fellows cannot make any change. And if something goes wrong, they have to call them. Okay? So they can't do anything. That's the way it is. Okay? That is the one that makes it expensive. And one of the reasons why this is expensive is very few companies in the world have a monopoly on that. And there are no Indian companies doing automation of this nature. Robotics also, there is nobody in India. So this is just to know that although robot programming appears to be very easy, but at this kind of programming, then you should not try it. Okay? It's extremely dangerous to do. And very specialized people, specialized companies do this kind of programming, and that adds to the cost. Okay, so I think this much is enough for our basic programming experiment, so which we'll be doing in the afternoon today. Yeah. So on the same assembly line, they will not be making different vehicles. It will be the same vehicle. So every assembly line is dedicated for that vehicle. So yeah, to answer your question, I have to go back a little bit. That if you look at, I don't have it here. So if you look at, if you draw, you would have seen this graph. So we'll cover it in more detail as we go along. But this is the manufacturing graph. So this is the part variety. You would have seen this graph, and this is the number of parts. Right? In any industry, you can classify it based on the number of parts it is producing, number of, I wouldn't say parts, maybe components. Okay. So for example, car company, the number of cars it is producing. Okay. This is the x-axis. Now the number of cars would be very large, say about 1 lakh cars at least. Okay. So this is the number of cars which have been produced. Now this is the variety of how many different. So if this is large, this will not be very large. It will be somewhere around here, maybe 10 kinds of cars, okay, or even less than that, maybe 5 kinds of cars. Okay. Now the the part variety is very large. Then we are going higher and higher, and this is like hundreds different kinds of cars it is producing. So one axis is the number of parts and the components, and the other axis is the variety of the number of those it is producing. So based on this, you can classify the industries based on whether they are what kind of industry. This is manual basically. Okay. So manual is here, flexible is here, flexible or what we call programmable, and this is hard automation. So the number of parts, number of components, and are very low. The other side, where the numbers are very large, but the variety is very small. So this is the other extreme. Okay. Now this is somewhere in between, so where it is here and it is here. Okay. Now in this industries, okay, where would you use robots? So robots using robots here. Okay. So robots cannot. Other side here, the large number of parts are there. So hard automation is much easier here. Something like transfer lines, pick and play, just normal your hard automation devices. Okay. Now, so here also robots are not used except for things like spot welding, spray painting. Okay. Otherwise, it is not economical again. So simply, if a part has to move from one place to another place, what they'll be using is indexing or simply transfer devices, but not robots. So robots are only available here. So if your parts are not very large, but they are somewhere here, maybe 50,000 or so, part variety is not much, but there is some part variety. You can flexible manufacturing, flexible automation that comes in here. Okay. So robots are not used normally fully here, not used here at all, but they are used mainly here. And the logic is that if you have to reprogram it, that is where the cost is. Okay. So there is no point in putting it here and changing the program every day. So this is something we, as we go along, we'll see that robots are essentially used there. Okay. So manufacturing, NC, CNC, all this comes in here, programmable automation. So this is where we use robots. Okay, let's move on now a little bit. Now we are coming to the structure. Let's talk about the structure. So till now we were talking about kinematics, a little bit of transformations and all that. But if you have to come to the labs and do and make robots by yourself, then we need to talk about then we'll have to talk about the controllers. The robots are actuated is we have a joint, and each of these joints are connected with a motor, which is an actuator, is a motor. There is a gear in front to increase the gear ratio, and there is a position sensor like an encoder at the back. Okay. Each of this has one compact unit. So each of this will be having one unit, will be coming as one unit, and this is called independent joint control. Okay. So each of this will be one, so there will be one more here, motor, gear, encoder, and there will be one more there. Okay. And this will be connected to a PC or a microcontroller or whatever, and it will be controlled. Now, why is it called independent joint control? Because each of these units are independently controlling one joint. There is no connection between them. Okay. And that is what makes robot control difficult. Why does it make it difficult? It's because if this fellow is not moving, but only this is moving, then this will have some velocity theta 1 dot. Now, this velocity will start propagating in that direction. Okay. Which means if I have, this is two links, this joint this is a revolute joint, this is also a revolute joint. Suppose this joint is not moving, only this joint is moving. So this joint is moving, but this joint is not moving. So as far as the controller is considered, this joint is not moving, so it does not require a torque. But because this fellow is moving, all the velocity of this fellow will also come here. So the velocities will start propagating, so velocity will start going in that direction. So this velocity will affect this velocity. in this way. So the velocities propagate like this, the forces propagate like that. And the poor controller has no way of knowing what is the effect of velocity from here to there, because they are independently controlling each joint. So if this joint is not moving, then the controller feels that no torque is required, it's not moving, right? But in reality, what is happening, this fellow's, what we talk about in terms of dynamics is that this is a coupled system. Where is the coupling? Every joint affects every other joint. Okay? And this is a fully coupled, nonlinear coupled system. And that is what makes robot control very, very difficult. Okay? So as we go along, we'll be seeing. But before we reach till there, let us proceed a little bit to see that each of these joints are actuated by a motor, which is an actuator. You have a gear in front, and there is an encoder for position feedback here. Okay? And each joint is actuated by one unit of this. So next, what we'll have to look at is sensors and actuators. So this is the basic feedback control loop for each joint. So you have an actuator there. So there is a controller, which can be PC, it can be microcontroller, it can be whatever, DSP. There is an actuator, which is a motor in this case. And this one is a work table in the case of NC machine, or in the case of a robot, it is welding. Right? So we have controller, actuator, link or work table, and we have a position sensor, which is an optical encoder. The optical encoder will give the position information, and then it will come like this. This is my feedback control. It's a very basic feedback control. Now here, how does it work? Suppose I want to move this work table by x units in this direction. Then I'm going to give a value of x, say x is equal to 10 units. So the controller will be taking input x is equal to 10. It will be seeing what is the position of this table from the position sensor. Suppose it is say 2. So the input from here, the feedback is going to say that the table is at 2 units now. So what the controller will do, it will do this minus this. So this is the summing block which does this minus that, and it will do 10 minus 2, which is 8. It will amplify that and then give it to the actuator. The actuator will start moving in this direction. So when this is moving in this direction, this value will start increasing. It will start indicating that the table value is increasing now. So this is my feedback which is going there. So what the controller is essentially doing, it is generating an error between this desired and the present, multiplying that with some gain, and then giving it to the motor. The motor is moving, this is moving. The moment this becomes equal to that, input here will become 0, and then it will stop, means it has reached. So that is essentially how a PD controller or PID controller works. It generates an error and then drives the actuator to make the error equal to 0. Okay? That is, of course, easier said than done, but that is how it works. That is the basic thing. Now, in this feedback control system, or this feedback loop, we see that what is this and what is that. Now, this is an actuator. So actuator converts energy from one form to another form. So here it is converting electrical energy to mechanical work. Okay. Now, what is an encoder doing, or position sensor? It is converting mechanical energy into electrical energy again. Okay. So this is electrical to mechanical. This is mechanical to electrical, and this fellow is always electrical. So if we ask what is the definition of an actuator or a sensor, actuator or sensor is essentially an energy conversion device. An actuator converts one energy to another energy, and sensor essentially converts again energy back to another energy. Okay? So the fundamental definition of basic definition of sensors and actuators is energy conversion from one form to another. Okay? So here it is electrical to mechanical, here it is mechanical to electrical. Why? Because this fellow only understands electrical, it doesn't understand anything else. Similarly, you can have pneumatic controllers, you can also have hydraulic controllers. Okay? In that case, this is going to be a hydraulic loop. But essentially, it is energy conversion. Next is, we talked about the size effect. If you make it smaller and smaller, then after a particular size, this will not work anymore. Right? So there is a size after which this kind of actuation doesn't work. And that is what we call the size effect. So if you make it very, very small, it won't work. Then you have to use something else here. You have smart material-based actuator or whatever. So in the micro domain, this loop doesn't work like this. The actuator is changed, and what we have is a smart actuator. Okay, so so the basic elements are sensors, actuators, controllers, and a system model. So basic elements of the control system that we have. Now there can be two kinds. There can be open loop, in which we have a controller, actuator, and a process. There is no feedback here. And there is a open loop system or it can be a closed loop system. Now, looking at sensors first, sensors are generally classified into two groups. One is an internal sensor, the other is an external sensor. So, internal sensors are required for the basic working of the system. So, for example, the robot that I drew there, for the PID controller to work, it must know what is the position of that joint at every instant. And that feedback is coming for the encoder which is here. The encoder is telling the controller where is that theta. Okay? So, this is an internal sensor. So, internal sensor is required for the basic working of the system like position, velocity, acceleration. And then there are, so without these internal sensors, the robot cannot work. Without internal sensor, it cannot work. Now, there are also sensors which are external sensors. For example, there can be a force torque sensor there, there can be a camera mounted there. Now, these are external sensors. So, external sensors are required for interaction with the environment. For example, vision, force torque. Now, if some of this goes bad, the robot will not die, but it will still work, but the interaction with the environment will come down. So, for the human beings also, we have internal sensors and we have external sensors. Right? In our body also, we have internal and external. Internal are what? Internal sensors measure your heart rate, blood pressure, temperature, that is being controlled internally. Okay? And external sensors are what? The external interaction with the world. For example, vision, hearing, speech, these are external. Right? So, we also have internal sensors and external sensors. Similarly, the same classification is there for the robot. There's internal sensors required for the basic working of the robot, and external sensors are for interaction with the environment. Okay? So, the essential sensors that are used for position loop are the potentiometers, encoders, LVDT, tachometers, accelerometers. External sensors are force, torque, pressure, slip, proximity, vision. So, this is the first type, potentiometer. You would have all studied in high school. Okay? All of us have studied. So, essentially it works by the principle of difference in resistance. So, the robot joint, if I put a potentiometer there, so what we'll do is we'll take the link and fix it onto the wiper. So, when the link rotates, this one will rotate. And the ratio of the small r to the capital R, we can calibrate it. So, if this is my 0, that is my 180. And then based on that calibration, we can actually figure out which position this one is. Right? So, this is a sensor which is not very widely used. It is very cheap, but it's very bad in the sense that there is a lot of noise, it's not very accurate, but it's very cheap, it's about 100 rupees only. But for simple applications, it's okay. Now, the one that is used extensively is the optical encoder. So, 99% position sensing devices in PID controllers will be using this optical encoder. And how it basically works, the working principle is very simple, is it is a ring in which there are slots which are cut. So, on one side we have an emitter and on the other side we have a receiver. So, it is something like this, where if I take the of that, so this is my optical encoder, this is my shaft. So, on one side we have an emitter and on one side we have a receiver. So, this is my emitter, this is the receiver. So, whenever light goes through, it gives a reading of 1, and whenever there is no light, it gives a reading of 0. So, what we get is 1 0 1 0 1 0 1 0 like that. Okay, so, the working principle is very, very simple. So, this is a plastic ring in which there are slots which are cut. And there is one emitter maybe on that side, and there is a receiver which is a photocell on this side. So, whenever light goes through, whenever it is transparent, light will go through. So, it gives a reading of 1. 1 means it gets some voltage, 2 volts. Whenever there is no light, it is 0. Right? So, when the joint is rotating, so we get joints in the back. Okay. Well, so there is no other conversion required. The controller can actually. Okay. Now, how do you measure the position? So, if this one rotation is 360 degrees, and if there are 200 cuts in there, then it is 360 by 200, which is about 1.8. Okay. That means the distance between one signal to the other one, so from here to here, is about 1.8 degrees. Okay. Right? So, this encoder is, in terms of cost, it is absolutely almost as good as free. So, this is just a plastic strip, it doesn't cost anything. Okay. There is a small emitter and a receiver, and the signal output is a digital signal. Okay. And that is the reason why 99.9% cases is this one only, because it is free, because of the advantage. Now, the disadvantage of this being is that if we have 360 degree rotation and you have 200 slots, then your accuracy is 1.8. So 1.8 is not much. Okay. So what is done in industries or industrial applications is at the back of the motor, there will not be one encoder, but there will be more than one encoder parallel. Okay? So we have one encoder here, another one here, another one here. So if I draw the side view, okay, so we have one encoder. So this, the slots are cut. So there is one more at the back, and there is some phase shift between the slots. Okay, they are not aligned. So this is one encoder 1, this is encoder 2. So this and this are not. When we get the signal output, if this is encoder A, it will give you the square waveform that is 10, 10, 10. The one at the back will give another square waveform, but because there is a little shift between these two, this fellow will be lagging or it will be leading. Okay. So we have one signal from one encoder, the one at the back is this one. If we have one more, there will be one more. So if I use the XOR gate, A XOR B, then what we can do is we can XOR the signal of this and get this signal. Now XOR gate essentially means that if there is any change in signal here, there will be a corresponding change on this signal. So any change on this signal or this signal will create a change here. So if you see here, it is constant, it is constant. Here there is a change in this signal, so immediately this one has changed. This one is constant, it is constant. Then around here, this signal is changed, so this fellow will come down. So if you look at how close these two waveforms are, if this was 1.8 degrees, this will become half that. Okay. Essentially, by using two encoders, we are increasing the resolution 2 times. So if I have 3 encoders, I can increase it more number of times. So industrial applications will be having number of encoders stacked in parallel, and then they are going to increase the resolution simply by doing the XOR gate. In the earlier days, there used to be a computer mouse. Now the computer mouse is optical. In the olden days, there used to be a mouse, and in the back of the mouse there was a ball. I don't know how many of you have used that or remember that. So if you take out the ball, you can actually see that, so there is a ball at the back of the mouse. And on the side of the mouse, there is a roller here, and there is a roller here. Right? And on the roller, there was an encoder here and an encoder here. So there is an emitter, receiver, emitter, receiver. So when you move the mouse, what happens? This is in contact with the ball. So this one rotates. If you move it like this one rotates. That's how it used to sense position. The olden day mouse. Now it is optical. So exactly the same principle is used in measuring measuring position using an optical port. Okay. Now this is very, very cheap, and because of which almost all position measuring devices, not only in robots, anywhere we are measuring position. Okay. Position controllers for motor control, then aircraft control, any kind of control is using this one. So this is another experiment we have today, where you have to actually take the signal with a microcontroller, read it, and then control a DC servo motor. Okay. So we have a DC motor. At the back of the DC motor, there's an encoder. This is an industrial motor, and we can read the signal using a microcontroller input channel. From one channel, you can take the input and simply check when it is high and when it is low. Okay. Now, depending on how many highs and lows are there, that is the angle by which it is moved. Okay. So if you want to control the motor, move it to some position, you know exactly how many pulses should be there. So it can count those many pulses and stop when it reaches. Okay. So this is one experiment we have today in the afternoon, where you have to control the position of a motor by using an encoder with a microcontroller. Okay. Now, in terms of the feedback loop, we require the position, we require velocity, and we require acceleration, because the controller needs all those things. Now this is giving me the position, because I know the distance between both of them. How can I get the velocity from here? So we know this is the distance. So if I know that how much time it took to go from here to here, I can do this by a dt. So I can get incremental velocity, right? So this is not only giving me position, it's also giving me velocity. Okay. Now how do I get acceleration from that? Where you take the second difference. Okay. So you take the second difference, so you get velocity, you get position, velocity, and acceleration. So this device, which doesn't cost anything, is actually giving you position, is giving you velocity, is giving you acceleration. So any controller which uses position, velocity, and acceleration makes use of this only, and can use all kinds of feedback control systems. Very complicated ones with feed forward, velocity feed forward, and also uses this one. because from here you can get velocity and position also. Okay? And that is the reason why 99.9% position measuring devices are this one. Now, the only problem with this is that it is an incremental device, so there is no absolute position. There is no absolute zero here. The second point is, if it is rotating this side or it is rotating that side, means clockwise or anti-clockwise, the signal is going to be the same. So how does the controller figure out what is the direction of rotation? So if you have one encoder like this, the signal always will be 10, 10, 10, irrespective of whether it's clockwise or anti-clockwise, doesn't matter. But the controller must know whether the motor is rotating clockwise or anti-clockwise. So what is done is, instead of one emitter receiver pair, we have two of them with a little bit of phase shift. Okay. So there is one emitter receiver here, there's another emitter receiver there. And depending on the phase shift, which one is lagging and which one is leading, it can figure out. And then from that it figures out whether it's clockwise or anti-clockwise. Okay. So an industrial motor controller would have an encoder with two emitter receiver pairs sitting very close to each other with a phase shift. And based on that, you can look at the signal and then say that which side it is. Absolute encoders are almost similar to incremental encoders, only difference being that instead of one rack, it has two layers, four of these rows, and each one will give a 0, 1. Say for example, if this is 1, 1, 1, this will give 0, 1, 1, 1. Exactly like an incremental encoder, but there are 4 rows now. This is absolute. This is not used anymore. Why? Because it is expensive. Okay. If you make 4 rows, there has to be some kind of signal conditioning now. There has to be some kind of logic which will figure out where it is. Okay. That's why this is not used. This is rarely used. Motors, you are familiar with on-off switches. So these are some of the sensors which are commonly used. This is a proximity sensor. So if how it works is essentially very, very simple. So there is a magnet and there is a coil in front. Now, under normal condition, the magnetic lines of force will move like this. Now, the moment something comes in front, the ferromagnetic part comes in front, the magnetic lines of force will be pulled out because of induction. So the magnetic lines of force are pulled out now. The moment the lines of force are pulled out, they will cut the coil. Now, if they cut the coil, they will induce an EMF. Okay. So the moment something comes in front, you will get an EMF in the coil, and that indicates that something has come in front. Okay. So we talked about when an object comes on a conveyor, some sensor is used. So this kind of sensors are used for checking when an object has come in the industry, when the object is gone. Okay. So very simple on-off kind of sensors are used. Hall effect sensors, again exactly the same procedure. This is a Hall effect sensor. This is the magnetic lines of force. And if nothing is in front, the lines of force are like this. If something comes in front, immediately lines of force are pulled out, so they don't pass through this anymore. So this is an off condition. This is an on condition. So this is essentially saying that whether there is something in front or there is nothing in front. Okay, so it's a proximity sensor, right? But your question is interesting in the sense that sensors and actuators are used everywhere these days, everywhere. Okay. So when it's measuring, when the speed in a car is being measured, how is the speed in a car being measured? When you sit in when you drive a car, there are two dials. One is showing the engine RPM, the other one is showing you the RPM of the car, the speed of the car, and one of them is showing you the speed of the engine. How is that being measured? Tachometer, no. Motor. Wheel, nahi. Because wheel is there is high chance of damage and all kinds of dirt and everything getting inside. Okay. So essentially, what is done is they use this the Hall effect sensor. Now this Hall effect sensor is a MEM sensor. It's very small. It's about 2 millimeter only, and there is no moving parts. So it's a solid state device. It's not very expensive. It's hardly 200 rupees. Yeah. So one is at the output of the engine, okay, and the other one is after the gearbox. So if you can think about this as a gear teeth, okay, then the number of when the gear is rotating, this is measuring how many on-offs are coming. Although it's measuring on-offs 1010, it's the same thing, and it knows how much time, so it knows the velocity now. So at the output of the engine, on the shaft, there is a small projection, something like this. And depending on when it is rotating, how many times that projection is coming. From that, it knows how many times it has gone round. So there is the counter. There is engine RPM. Now the wheel RPM is after the gearbox, right? So this sensor is also used for measuring the car speed. So in robotics, we can use it for measuring distance, proximity, but it can also be used. It is used extensively in other applications. Ultrasonic sensors. So ultrasonic sensor working principle is very, very simple. So there is a ceramic transducer. So we give it a particular charge. It will produce, it will vibrate, right? Ultrasonic transducer means piezo crystal. If you give it a particular charge in a particular frequency, this will vibrate and will give out an ultrasonic wave. The wave will hit a surface and it will come back. Okay? And the time duration for it to go and come back, from that we can figure out how far it is. For example, here, this is the driving signal. The wave is going out, it is hitting something and coming back. This distance, if we measure, then we know the velocity of sound in air. So essentially, from this time duration, I can figure out how far it went, and then it has come back. So ultrasonic sensors can be used for measuring distance, okay. And this is another experiment we'll be doing today, because mobile robots use this extensively, okay, for measuring obstacle in front, for measuring any kind of obstacles that come in. So the working principle is very simple. You just activate it in a particular sequence, check when the signal has come back, and from that we can figure out what is the distance. Okay. Now, yeah. So this experiment also we have in the lab today, which we'll be doing. So using this, you can make mobile robots and do all kinds of work for motion planning, obstacle avoidance, things like that. Now, the interesting part here is that if you ever work with mobile robots or this kind of sensors, one is that they are very cheap. This is not very expensive, just 200 rupees or something. Okay? But very often it will not see. What I mean is, if you have a mobile robot and I put the sensors in front and I leave the robot here, very often the robot will go and hit your legs and it will do all kinds of things. That means it is not seeing. Right? So under what condition will it not see? So we said that sensory signals sometimes can have errors, it can have noise, it can have all kinds of other things. So under what condition would this fellow not see, and why will it not see? It is within range, for example. So it yeah, but why? So essentially, the ray will go out like this, it will hit an object and then it will come back. So it will only come back if it hits normal to an object. If it hits at an angle, what will happen? The incidence angle will become the reflected angle and it will go somewhere else. Right? So if there is an object which is not normal, it will not see. So what kind of objects will not be normal? Curved surfaces, right? Any kind of curved surface it will not see. So for example, this bottle it will not see. Very, very high chance it will not see this at all. Okay? Because the reflected ray is not coming back. The second kind of surface it will not see is if the ray is absorbed, if the ray is not coming back. If, for example, this cloth absorbs ultrasonic waves. So if you are standing there, very often it will not see you. Why? Because the pants are absorbing the ray. So this very simple thing, costing 150 rupees, has a lot of implications, and so one of the implications is in defense. If you don't want to be seen, this sensor is about 200 rupees. So the previous one also, Hall effect is also about that much, 150 rupees. So this is 200 rupees. So if you don't want to be seen, then you know what is to be done. So in defense applications, all these aircrafts and ships, okay, that cannot be seen, because the radar works on the same principle. It gives out a wave, it hits the object and comes back. Right? So if it doesn't come back, it can't be seen. So all these ships and this aircraft that are what they call it the stealth technology they have a particular shape. So the shape is such that it will never be normal to the wave. The second is they use some kind of paint and material on top. That material absorbs all the rays. Okay. So although this 150 rupees thing has implications for defense also, which is interesting in the sense that this has a lot of use in defense, and this stealth technology is actually very expensive. Okay. So this experiment also we have in the lab. We'll be doing it, and post-hoc sensors. Now, in terms of actuators, we basically will look at electrical actuators, pneumatic, hydraulic, and advanced actuators. Electrical actuators are essentially stepper motors or DC servo motors, which you are familiar with. Pneumatic is air pressure. Hydraulic is fluid pressure. Advanced actuators are like ultrasonic motors, artificial muscles, molecular motors. Now, depending on the load carrying capacity of the robot or a particular joint, you could be using different actuators. For example, industrial robots which carry very heavy load, 50 kg, 100 kg, their base actuators are hydraulic, because that is where the maximum load comes. Okay. So hydraulic actuators are used for very high load carrying capacity robots. The base will be hydraulic. Second is, in between, there would be electrical, and the gripper would normally be pneumatic. So a robot could have hydraulic, electrical, pneumatic, or electrical, pneumatic, different combinations, depending on the load. The gripper is normally pneumatic, essentially because this piston cylinder mechanism for a pneumatic system is safe. So if the robot were to hit something, okay, if you have a motor, like you have a gear, this is not back drivable. You cannot drive it backwards. So if it hits something, something will break. Whereas a pneumatic system, a piston cylinder can just go back. So a lot of the robots today, which we call safe robots, are pneumatically actuated. Okay. So all the robots interacting with humans and things like that, a lot of them are pneumatic actuated because they are safer. This is more powerful. This is more powerful. That is less powerful. That's only. Working principle is same. So stepper motor, you would have again studied this. So essentially, it works in steps. So we have a stator and we have a rotor. So depending on how we are actuating this, so if I actuate this this pole, what would happen? This fellow will get attracted by magnetic induction. Okay. So there is a permanent magnet stepper motor in which if we actuate this one, this will get attracted. Then if I actuate this one, this will get attracted. If I actuate this one, this will get attracted. Okay. So based on that, it can move in a clockwise, anti-clockwise direction simply by sequencing the activation of the pole. Okay. This also experiment we have, which you'll have to do, write a program and then use microcontroller to control. Now the advantage of this is that it's an open loop device. It's moving in steps, so you don't need a feedback for this. So it is cheap. Okay. The only disadvantage being that it's very heavy. DC motors, you are familiar with. Brushless DC, essential difference being that in the brushed motor, the coils are inside, in a brushless motor, the coils are outside. Here you do electronic limitation. That's the basic difference between this and this. Now, one kind of motor is becoming very popular now, is this servo, in which in one package, okay, we have a motor, we have a gear, we have a potentiometer, and we have the PID controller also in one package. Now, this is very, very useful, because if you have to make a controller using a brushless DC or a brush motor, you need an amplifier, you need a converter, you need a PID controller, it becomes very expensive and difficult. Okay. But once you have this ready-made coming in a box, and this is already pre-calibrated, then you can control the position very, very easily. Okay. So this has a gear. So what we need to do is simply mount the link here, and depending on how we are controlling this, that will come to, you can use a motor. So a lot of the lab experiments today, okay, for students, for projects, can be made by using this, and they are cheap, 450 rupees, 500 rupees. Okay. They have pretty good torque, pretty good resolution. So the cost of things, what we say mechatronics or making small robots, small devices, has drastically come down today. The microcontroller, either Arduino or Atmega, is about 500-600 rupees. This fellow is 500 rupees. So you can make a 4 degree of freedom robot in say 2,000-3,000 rupees. That is enough to teach forward kinematics, inverse kinematics. So this is something you'll be seeing in the lab, how to do that. Okay. all the programs, you'll have to run the program yourself and see how the program works, how the controllers work. So that after you go back, for lab experiments, even here, we build robots and we use robots like this, so the students can actually see what is happening, and they're familiar with the actuator, sensor, controller, and they can design different robots and play with it. So this is basically called a servo, and it consists of these 4 branches, and it is made such that you can control the position. Normally, you can control it from 0 degrees to 180 degrees or 270 degrees. How? We'll see. So this is another experiment you'll have to do in the lab. And controlling this, you can attach it. For example, if I make a serial link, just put 3 servos, and you can control it using a microcontroller. So this is one experiment which will be doing. Now, just closing off quickly is, if you want to go to a different scale, for example, if we are going for a micro device now, then we cannot use a DC motor or a servo motor because we can't make it very small. Then we have to use some other kind of actuator. And there are other kinds of actuators, for example, ultrasonic motors, artificial muscles, molecular motors, to go to a different scale now. Now, how this works is, ultrasonic motor essentially works like this. We have a rotor and we have a stator. Now, in the stator, this is made up of piezo crystals, and this is the rotor, and this is in physical contact. Now, how it works is, this fellow being piezo, if you charge it, if you activate it in a particular sequence, in a particular frequency. So here, if I charge this one, what will happen? It will give a small kick there, or a small push there. It will move this side. So I'll activate this one, then this one, then this one. So what will happen? This fellow will move in that side. If I reverse it, it will move this side. Okay. Again, you have used this. A lot of the sensors, actuators are there in cars, are there everywhere today. You might not have noticed them. This is the way all the cameras, the autofocus mechanism in the camera, they all work using ultrasonic motors. So you would have used cameras in which the lens moves. Okay. Either digital camera where the lens actually goes front and the lens comes back, or a big SLR camera. Okay. So there, on the lens, you would find that there is one fitted onto the lens and this fitted on the camera body. And it works exactly like this one. So this is piezo, so it is independent of size. You can make it very small. Again, this is a little expensive, but not that expensive. It's about a few thousand rupees. But it has very high torque, and you can get very small size. So making small motors, small robots, can be made using this kind of actuator. Yeah. So if you activate in this sequence or in that sequence, you just reverse. Yes. Now this is in physical contact with that, and there is friction there. So the torque of this motor is very high compared to a DC motor. So the torque of these motors are much more than DC motors. But they work in steps. So if you carefully notice when a camera lens goes out or it comes in, if you have noticed, it moves in small steps, very discontinuous motion. So that is an indication also that the motor inside is not DC servo. It is something like this. The other is electroactive polymers. So these are polymers. If you give a particular charge, they bend in a particular direction. Again, these are independent of, so I had shown this slide earlier. These are independent of size. So if I cut it and make it smaller, it will still work like that only. So when we are talking about micro devices, nano devices, we talk of flexible mechanisms today, flexible robots, active vibration control. So all types of research issues are there. Where you cannot use a DC motor, we can use this kind of thing. Okay, so either this or this. So either ultrasonic motors, then the other is SMA, smart material shape memory alloys. So this table basically shows the other kind of actuators. One is ionic polymers, shape memory alloys, and electroactive ceramics. So depending on the force requirement and the displacement requirement, we can choose which actuator we want now. This basically has to do with size. So if you're going to micro domain, nano domain, flexible domain, then instead of DC motor, we can choose one of this, and based on this table, we can choose what we want. Okay? So some of the experiments are there in the lab. So as we go along to the experiments, it will become more and more clear. Okay? So let's break for lunch now. So what we'll do is we'll meet here at 2:30. Okay, because today we are going a little slow. And in the lab, you'll have to use microcontroller. So how many of you are familiar with microcontrollers? Well, 5, 6. So what we'll do is very briefly, say 10, 15 minutes, I'll just introduce microcontroller. It's very simple. And then we'll talk about things like PWM, how to control a servo using PWM. Okay? And then we'll go to the lab. Because in the lab, you have to use a microcontroller, do the program. Okay? So we have made some groups also. Outside in the notice board, the groups have been put, who is doing which experiment today. Okay? And in the experiments, it is supposed to be hands-on. So first you see how the program runs, how the hardware is connected, what is the hardware, for example, an encoder, how the signal is coming to the microcontroller, how it is controlling. Then you can change parameters and see yourself. And at the end, you can take all the programs so that if you make the device yourself, you can run it again. Okay? And most of the things are very cheap. Sensors, actuators are very cheap these days, 300 rupees, 400 rupees. So you can build a good robot in 5,000 rupees. So there is a 4-axis robot which is hardly 5,000 rupees. Planar is 2,000 rupees. So that will be useful for you for teaching and for labs and all later on. Okay. Okay. So I'll basically cover what is required for the experiment. Okay. So this is not in any way a detailed explanation or lecture on microcontrollers. So somebody will be talking about microcontrollers later from electrical engineering, Professor Das, probably tomorrow or day after. He'll give you the details of microcontrollers, how microcontrollers progressed, what is a microcontroller, programming, and then there is a lab, of course. Let's explain about what we need for today and tomorrow. So what we'll be covering today is basic programming of microcontrollers, sensor interfacing. So when we are interfacing a sensor with a microcontroller, what it basically means is that it will have to read the sensor like IR, infrared, or ultrasonic, okay, or encoder. These are sensors. Okay. So when a microcontroller reads these sensors, how does it read the sensor? And what do you do with that information? Then, so this is one set of experiments. The second set of experiment is motor control. So DC servo motor control would mean position control of a DC motor using encoder. So the encoder will be interfaced with the microcontroller, and if you want to control the DC motor to a particular angle, for example, then we just have to read the number of pulses that have come from the encoder, and based on that we can get it to the get a particular position of the DC motor. Then DC servo consisting of a gear, motor, potentiometer, and a PID controller. How do we control DC servos using PWM? Then encoder interfacing. Okay. So these are some of the experiments, plus there are other experiments like Puma robot is there. Okay. Those we'll be doing today. So just fundamentally what is required to do the experiment that I'm explaining. Okay. Details will be covered later. So the microcontroller we'll be using today is the Arduino board. Okay. So this one, it consists, so this is a board basically. So it has a microcontroller which is the Atmega 16 or 32, 16-bit or 32-bit microcontroller, which is this one. It has peripherals like it has ADCs inbuilt. It has channels for PWM, okay, inbuilt onto this board. So this is some kind of a hardware by which you can do very simple sensor interfacing, motor control. So we can actually control this, control a very simple robot using this itself. And we can write our forward kinematics, inverse kinematics, code it in here, and run the robot. So we have two robots today, which we have made for students to understand. One is planar, something like this, 2 links to do forward kinematics, inverse kinematics. But that is also controlled with this one. So so this is basically an open source hardware which consists of an Amtel microcontroller Atmega 1632 based programmable circuit board, and it uses a very easy software ID integrated development board that runs on a computer. So the basic GUI based kind of you can program it using a GUI based kind of a software. Okay. Now in the earlier days 8085 in assembly language. So this is modules for being to do is just those. Okay. So we'll be basically be using this board today, and the cost of this board is about 600-700 rupees, okay, which is very cheap and is very powerful. It's 3 megahertz processor is there. Okay. So it is quite powerful and enough speed to control a robot for doing simple industrial robots, of course. Okay. So what we'll be basically doing is we will connect different sensors, different encoders, motors to this kind of a microcontroller, look at the program interface, try and understand the program, how this is working. Okay? And then if you want to make any changes on that, you can make the changes and then you can see what is happening on the other side. Okay? Now how do we download it? So essentially this is running on your PC or your laptop. So there is a download from here. You can simply download it. So it will convert into the ASCII language, ASCII code, and then download onto the driver. Okay, so you don't have to do the programming in assembly language anymore. Okay? All you can do is write in a higher level language like this. It will do all the conversions, download there and start. Okay, so it's very, very simple. Now the basic microcontroller has a number of pins. Okay, this particular one is the Arduino pin diagram. So this is the pin number you can see, which is written here: A1, A0, A2, A3, A4. So these are pin numbers. This is ground. This is voltage in, V in, the power into the microcontroller, which is 5 volts. Okay. This is the ground. Then there are other pin numbers: 8, 9, 10, 11, 12, 13, 14. Okay. Then it is 1, 2, 3, 4, 5, 6, 7, 8. These are digital pins. These are analog in pins. This A stands for analog, D stands for digital. Okay. This is the channel number. So you can consider this to be a channel. So if I connect a wire here, a sensor here, onto A0, then basically I'm connecting the wire from the sensor onto A0 pin number, and it understands that whatever is coming in from there is coming as an analog in. Okay. So I can convert that into digital using ADC and then record it and keep it or do something. Okay. So the basic, which the colors indicate what it is doing. Okay. So this light blue color is a digital pin. The green color here is an analog pin. Power is given here, power ground, which is power to this guy. Then serial interface is by this one. Then the others are PWM is the red color. These are PWM pins. PWM stands for pulse width modulation. So we can control DC motors using PWM signals. Interrupt is interrupt 1 and interrupt 0 are these two pins. Okay. So this is the basic layout of the board, and you can correspondingly attach sensors via wires onto this particular number of channels. So when we said channel number, when we talked about valve programming, this is what I mean by a channel number. Okay. So each of these channels have particular functions and they have particular names, okay, particular numbers in this case. Okay. So so how we are going to start? So in this microcontroller, we can have an input. That means something is coming to the microcontroller, or we can have an output when you want to think outside. Okay, so we are controlling a sensor reading, which I want to take into the microcontroller. Then it's an input channel. Now, if I want to give something out, then it becomes an output channel. Okay, that is essentially input or output channel. So we can define the channels. We have to set the channels as an input channel or an output channel, depending on what we want it to do. For example, if I want to glow or burn an LED, then in that case I will connect the LED to a particular channel. Okay. So I'll connect the LED to a particular channel, and in that channel will be an if I want to glow it, it will be an output channel. Okay. So it will be out, say 5 volts. So on that channel 5 volts out will go. So we have to set the channel numbers, or in this case it is called pins, as input or output in the first. So pin default setting is input direction, default is input. Okay. This is the default. So as soon as you power it up, then you have to set it to output, otherwise it will be remain as input pin. So the first thing that we need to do is we need to define the pins, whether they are input pins or they are output pins. That's the first thing we need to do. Now the pin voltages that are there is basically a low, which is 0, or it's a high, it's 5. Now depending on whether it's a CMOS, then it can be 3.3. This we don't need to worry. So essentially low means 5 volts and high means 5 volts. Low means 0 volts and high means 5 volts. And this is using PLT logic, which is transistor logic. Let's not worry about all that. It will be covered later. Okay. So a high essentially means 1, or a low means 0. So I start off by saying my pin is an output pin or an input pin. Then I say that particular pin as a high or a low. Okay. So I want to give a voltage out, 5 volt out, then I simply say that pin number and high is 1. Okay. So 5 volts will go from that channel number out to whatever device is that side. Okay. So high and low is defined by 1 or 0. In in terms of logic. Now, what is the syntax? So, in the language that we are going to use, that I had showed some time back in the GUI that is running on the PC or the laptop, will be this one. So, each of this will be having a statement, okay, and it has some syntax. So, it says digital write, pin number high. Okay. So, what is the syntax? The first syntax is, yeah. So, the first is pin mode. Okay. So, this sets the pin mode to either input or output. So, pin mode is the syntax. This is the pin number. This is the pin mode, input or output. So, in the beginning of the program, we are going to set each of whichever pins we are going to use to whatever direction we want it. So, pin number, so it's input or output pin. Okay. Then digital read pin. This is we are taking something into the microcontroller. Okay. So, these are read pin. So, we are saying digital read and pin number. So, reads high or low from a particular pin. So, digital read and this is the pin number. Okay. So, as you can see, the syntax is very, very easy. Then digital write is a pin number and a value. So, value can be high or it can be low. So, this is a pin number and there is a value which is high or it's low. Okay. Then analog read pin. Analog read is a pin number, whichever pin is the analog pin. We saw that A0, A1, A2, A3, those are pins for analog read. Analog write pin, again pin number, value. Now, this analog write can go, takes a value from 0 to 255. So, it can take any value. What this means is that I want to power an LED. I have the option of giving the full voltage, or I can break that voltage into small amounts and give also. Okay. So, this is an analog write and it takes values between 0 to that. Now, so the basic Arduino main program consists of two loops. One is this one, okay, and the other is this one. This is the library function for the microcontroller for setting up itself, its own functions. Okay. So, this is the one that is going to do all its internal functions by itself. This is the one that you are going to write. Okay. So, these ones are basically header files which you can put different header files there depending on what you are using, and the program you will be writing will come in here now. Okay. So, these are the various loops that, so things like input from sensor, sending output, that will come here. This is a part of the controller itself. LED blinking, a very simple experiment is there is an LED there and you want to blink this LED. Blink means turn it on, turn it off. So, the program that looks, this is the top part. So, pin mode 13 is output. So, pin mode is setting the pin mode of number 13. Now, in this the LED is connected to number 13, it is inbuilt LED. It can also be an output LED from outside. In this particular case, the LED is a part of this board and it is assigned, internally assigned a number 13. We are saying this is output port. Then we say digital write, LED built in, which is this one, okay, and we say high. Then we give a delay of something, okay. Then we give LED, so LED built in is again an internal function. So, this is a built in LED, so it understands this is this one, otherwise it is a pin number. Here it is internally assigned that this is equal to that. Okay. So, we simply say digital write, LED built in high, which means 5 volts. We give a delay of 1000, means it will remain 1000. Then digital write low, then we give a delay of 1000 again. So, this is an infinite loop, so it will keep going in that loop. Okay. Is it okay? So, this is the simplest you can have, and it is also very, very simple. There is nothing to understand here, right. So, this is basically an experiment for, not experiment, this is a program for LED. In this particular case, our LED was an internal LED of the board itself. We assign the number as the pin mode as output. Then we say build LED built in, high, low. We can change this time and then keep increasing, decreasing, delay, and it will do all kinds of things. Okay. So, this is one example. This is another one, which is blinking two LEDs now. One will go up slowly, the light intensity. The other one will come down slowly. So, we have two LEDs now. In the previous case, it was just 5 volts on and 5 volts and 0 volts off. So, it will come full power and it will go off. In this case, what we are doing, we are having two LEDs, okay, connected to channel numbers 10 and 11. And what we are doing is in one of them, we are slowly increasing the power from 0 volt to 5 volt. So we had seen that you can increase the value from 0 to 255 using analog writes. Okay. So here it is at a high value and is coming slowly to a low value. So from 255 to minus, minus, minus. That means one of the LEDs, the intensity of light is coming down from maximum to minimum, whereas the other one it is going from 0 to 255. So one of them is going up, the other one is coming down, and this is an infinite loop also. So it is just cycling, okay, until you stop it. Which one? Analog write is we could have just written write. Okay, here we want to cycle from this value to that, from 0 to 255 actually. So we are doing analog write. No, you can't do in digital write. Okay. So this is an example. This is Hall effect sensor we talked about in the morning. So this is a Hall effect sensor, and we have connected this sensor onto this breadboard, and from here we are taking the connection onto. Sorry, this is the power. So this is going onto that channel. So this is a pin mode sensor input. Pin mode LED is output, and this is a sensor. So we have two. One is a Hall effect sensor here, and the other fellow is the LED there. Okay. So what we are doing is, in this very simple experiment, if something comes in front here, okay, it should sense, and the moment it senses, it should put on that one. That something has come in between now. Okay. So in this experiment, we have a Hall effect sensor here, which is connected to your pin, okay, and the pin mode is LED is output, and this pin mode is sensor is input. And we can start assigning a value of val. Digital read is from the sensor it is reading, and whenever so when the serial print, it is getting some output from here. So as soon as something comes in here, what will happen? This will become high. The moment this becomes high, this will, if this becomes high, then it will digitally write. Okay. So when something ferromagnetic comes here, what will happen? This channel number will become high. Okay. And this is showing that if the value is high, meaning 5 volt, then it will write to the LED and make it high. Else, it will make it low. Okay. Oh, this is a rate actually. What rate? Rate. Yeah, so this one he probably wanted to see a display somewhere. So there are other options also. So this is all there in the lab, you can have a look. So you can change all this and play with this. That's the idea. Now we are coming to the microcontroller, the motor control part. Now what happens is that when you're running a DC, the DC motor would be requiring, this can give as an output a voltage from 0 volts to 5 volts, right? Now in this device, the microcontroller, it's a digital device, right? So it cannot give you an analog out in that sense, right? So one way of trying to do this analog out or trying to vary this voltage is by using what we call a PWM. Now what is a PWM is that it gives this square waveform. Now part of this square waveform is on and part of it is off, which is called the duty cycle. Okay. So what output is coming out from the microcontroller is this square waveform is coming out at a particular frequency, and each of this 75% is on, 25% is off. So if this is 0 volt and that is 5 volts, then the average of this will be somewhere around here, which is 3.75 volts. So by that way, we are varying the voltage, okay, from 0 volt right up to 5 volts in small increments, simply by changing the duty cycle here, right? So when we are controlling the servo motors, what we do is we change the duty cycle, and by this you can control a servo motor. Now the servo motors that we talked about in the morning, so this is my duty cycle. 0 duty cycle is 0 volts, 10% duty cycle, 25%, 50, 80, 100. Okay. So this is the way it is calculated. So duty cycle by 100 into 255. Okay. So what we do is something like this. Okay. So this is controlling a DC motor with a power supply. So what we do is we give an output from here to in terms of that pulse width modulation. Now the motor requires more current, okay, because the output current from here is very, very small. It's about 100 milliamperes only. That's not enough mainly to drive big motors. Okay. So what we need to do is we need to have a power amplifier. Essentially everything here is the same, only the signal is going here, it is getting amplified by the L29H. So that's a power amplifier. Okay. This power amplifier is giving the additional current that is required for the motor, and the motor can rotate. Okay. So for motor control, we can control this using, in this particular case, what we have done is there is a potentiometer at this end. Okay. Depending on how you rotate the potentiometer, the corresponding PWM signal will go on to that, get power amplified, and the motor will rotate. So you can control the speed of a motor simply from this potentiometer here. Now controlling the position of a motor, we talked about these motors, which are very, very common now. Okay. How do you control this motor? There is already a motor, a potentiometer, and a gearbox inside. So we connect the link of the robot onto this linkage. Okay. And there is a PID controller which is inside, which is pre-calibrated. So what it basically means is that when I'm giving the PWM signal, this motor can rotate from 0 degrees to 180 degrees. This output, I mean, not the motor, the output link. It is designed and calibrated in such a way that one end is 0, it rotates like that and goes to the other end, that is 180, normally 180 or 270. But this does not rotate fully like a DC motor. Okay. Now one end of it is 0, the other is 180 or 270, and the PID controller is tuned or designed in such a way that it is proportional to the duty cycle of the motor. Okay. So if I want to take it 0 degrees, I'll put 0 duty cycle. So it understands it and will remain there. Suppose I want to increase by say 5 degrees, then I'll increase the duty cycle a little bit more. Okay. So by that you can do position control of a robotic linkage mechanism very, very easily. So you don't need to get into the PID loop which is in there. We'll come to those later, but at the moment you don't need to know how the PID controller was designed. Okay. So simply by looking at the program, you want to move this by 5 degrees, you change the duty cycle, it will go 5 degrees, it will stay there. Okay, it will do it by itself. Okay. So these are, so you can build very simple robotic devices by using these servo motors. Okay. So servo motors, they are again not very expensive. Pretty powerful ones are also about 500, 600 rupees, pretty good ones. Okay. And microcontroller costs hardly 500 rupees. So you can build pretty good. So the program looks something like this. Now there are two ways. One is this my servo programs are already inbuilt, they are already freely available. So you can download this part, which are the header files, which has internal variables for the which is controlling the servo motor. Now you can simply change the parameters here in terms of the duty cycle, and then you can control it. The other way is you can write. So here we can see that these are the extreme positions. 180 degree is here, 0 degree is there, and 150 milliseconds neutral position is there. So depending on that, the duty cycle, whether it's a full, it is covering the full amount or it's not covering the full amount, the link end will go and stop. So this part is this part. So that part is this part. Okay. So what it basically means is that if you give a duty cycle this much, then it will go and stop there. Okay. If you give 0 degrees, it's on the other side, so 0 to 180 degrees, and you can control any point in between wherever you want it to stop. Accuracy is not bad; it's quite good. It's about 0.2, 0.3 degrees. So it's quite good for doing experiments. So this experiment also we have in the lab. So we have serial link, 2-link planar arm, and we have a 4 degree of freedom arm. So inverse kinematics of 2 degree of freedom has been done, right? Inverse kinematics of 2 degree of freedom has been done in, right? Inverse kinematics of 4 degree of freedom probably has not been done. Okay, but then we can solve it. So we'll show how to solve it. So one of the experiments is you have a point there, and I want to go. Suppose I'm here and I want to go to some other point. Then doing inverse kinematics, I can find what is the corresponding angle, and then whatever is the corresponding angle, I can see the equivalent PWM for that angle, and then give it there, and it will exactly go and it will stop there. Okay. So I can actually do motor control very easily without getting into PID controller design and all that, simply by controlling the microcontroller through a servo motor. Okay. Now the other experiments that, so these are some of the experiments. Sensor input output we have done, servo motor control is here, DC motor control is also there. Then yeah, so as part of the course you are supposed to do some small project. So as you are seeing the lab, you also think about what you want to do. Okay. For example, you can do pick and place by using a 2-link or a 4-link system, 4 degree of freedom system. Okay. Or you want to do, as we go along, vision will come in, computer vision. You want to interface vision with one of these robots. So first you see an object, Then you can figure out, you can do segmentation, take out the CG of that object. Then you can do the inverse kinematics and go there and catch it. Okay. So as you're looking at the experiments, what you should do is also think about what you plan to do. So on Sunday we'll have this project kind of. So Sunday is fully devoted to this only. What do you want to do? Okay. So those of you who are very familiar, you can take a higher level thing like vision-based integrated sum control. Okay. And those of you who are just starting, you can take something simple like sensor interfacing, control of tooling systems. Okay. Okay. Is that okay? Now in the lab, these programs will all be given to you. Okay. Given to you means we'll put in a pen drive and then you can take it also. Okay. And when you are doing in the lab, please read this and understand. Okay. Okay. So one way of doing an experiment is just press some buttons here and something moves there. Okay. The other way is you read this, understand what each of this means in terms of the encoder, in terms of the motor, how is it working, change some parameters and see what is happening on the other side. Okay. So that you'll get a good way of understanding this program. Then it will serve the purpose also. So when you go back, you can build very, very simple robotic devices. 2 degree of freedom we have built, 4 degree we have built, 6 degree also we have built using this only. So within 10,000 rupees, 6 degree of freedom is okay. Okay. So you'll see some of them in the lab. Okay, so I think that is a very brief introduction, or rather 2 brief introductions. More details will be covered by Professor S.P. Das, the details of microcontrollers, and then you'll go to the microcontroller lab where you have to see more advanced applications. Okay.